Good afternoon, everyone. My name is Aysha, and I'd like to thank you all for joining us on for the Minerals to Metals online forum hosted by the Southern African Institute for Mining and Metallurgy. It would appear that my video is cutting in and out. This is a problem on my side, so I'm just going to leave it off for now. Just to go through some quick Zoom etiquette. During the panelist presentation, please type your question in the Q&A section in the toolbox at the bottom of your screen. After the presentations, we will have a Q&A session to answer these questions, and at that point you can raise your hand and speak directly to the panelists if you wish. Please note that this forum is recorded and will be made available to the public. You can remain anonymous by changing your name and leaving your questions in the Q&A. If you have any issues or would like to be added to the mailing list, please send me a private message in the chat. I'm really pleased to announce our current presenter today. We have Professor Jochen Petersen, who is based at the Department of Chemical Engineering at the University of Cape Town. He is the South African Research Chair for Minerals Beneficiation and the Director of Minerals to Metals Initiative and the Hydrometallurgy Research Group. Just going to run through a quick impressive biography of his. He completed his PhD at UCT in '98 with his thesis on modeling of metal release from slag and tailings deposits. From 2000 to 2008, he was a research fellow at the University of British Columbia and UCT, doing research into heap bioleaching. From 2008 to 2018, he was a senior lecturer, associate professor, and professor, coincidentally at UCT, doing research into hydrometallurgy, focusing on heap leaching, alternative, very fancy, confusing word that I'm not even going to try, hence my my lack of technical knowledge is coming up, for leaching and copyright and platinum group metals, leach processes for rare earth metals, e-waste, ion precipitation, and ion exchange for wastewater treatment. Since 2018, he's been the SAIMM chair for minerals beneficiation with a focus on mineral mineral value chains, sustainability in minerals in the minerals industry, strategic minerals, and urban and artisanal mining. He has accomplished various achievements and co-authored over 220 peer-reviewed journals and conference papers, and he has supervised 9 PhDs and 45 Master of Sciences to graduation. He is also the editor-in-chief of the Journal of Hydrometallurgy. Jochen has joined us today and will be presenting on work that's been done within the low-cost extractive methods for the recovery of valuables from mineral wastes and the various opportunities available within the artisanal mining sector. I would like to now invite you, Jochen, to take us forward in the presentation. Thank you.
Thank you, Aysha, for the kind introduction, and just a small correction. It's only 120 papers, not 220. I hope one day I will get there, but that is still some way off. Okay, so I'm going to share my screen now to hope that okay, are we all set?
Yes.
Okay, so good afternoon, everybody. As Aysha has so kindly introduced me, my name is Jochen Petersen, and I'm currently the director of the Minerals to Metals Initiative, who are hosting this forum. In my capacity as the SAIMM chair for minerals beneficiation. And I thought I use the opportunity in today's forum talk to sort of summarize and reflect a little bit on the material that is being presented in quite a few of the foregoing forum sessions around various areas to do around the minerals value chain, and particularly in the context of wastes and artisanal small-scale mining. So I titled this talk, Low-Cost Extractive Methods for the Recovery of Valuables from Mineral Waste. Are there opportunities for small artisanal and small-scale mining? And the intention of this talk is really just to give, sort of set a scene and summarize a little bit the perspectives and detailed research efforts by many people who work in the context of the Minerals to Metals Initiative and beyond, to sort of map out how this all fits together with a vision going forward. So I'll start off with a broad introduction of the minerals process chain. And in here, in this particular context, I am particularly aimed at aiming here at a generic flow sheet to go through. We come from the mined mineral that is sent classically into a comminution, that's milling, crushing, milling, and fine grinding operations that can then or on to take the material into concentration processes such as flotation or gravity separation. And that concentrate is then handled essentially through a number of extractive metallurgical process routes. Probably you're all familiar with the sort of the classic distinction between hydrometallurgy and pyrometallurgy, but in practice, in most operations, you have actually a combination of both. And the question is whether really not the one can actually do without the other. So the concentrate can either go directly into a hydrometallurgical process, which are then so-called leaching processes that take place in tanks or under pressure in autoclaves, or the concentrate goes into a roasting process where it's either oxidized, the material is either oxidized or reduced at high temperatures, and the calcine or the reduction product is then secondary actually put again into a hydrometallurgical process where it's then leached and dissolved. So what you're doing is in roasting is really rendering the mineral phase of your target metal in the ore into a form that makes it soluble in aqueous solution. And then with smelting, the final route, the classic pyrometallurgical route, is where you actually melt down the mineral completely and effect a phase separation with or without reduction. You effect a phase separation between the material that you want, the melt, and the slag that you don't want. In some cases, you actually are making a sort of secondary product referred to as a matte, which again is then sent into a tank or more commonly autoclave leaching for further dissolution. Or you have the direct metal product, which is then may in certain cases, particularly copper, go through further refining steps such as electro-refining, or directly then go to form your metal products and byproducts that you want to achieve. Whatever comes out of the hydrometallurgical processing goes then, it brings the metals into aqueous solution. And then you have a series of purification and separation processes, such as solvent extraction, electrowinning, or precipitation that then yield final metal products as well and byproduct. Not necessarily in metallic form, they can sometimes be in the form of salts, but that is then a saleable or final product of the process. One particular route that is a little bit falls out of the classic route is indicated here on the left, where you have ore that comes straight out of the mine, or you have crushed ore that comes out of the first stage of comminution that you then put on a big pile for metal extraction. And that process is known as heap leaching. It is a form of hydrometallurgical processing. And I'll talk a little bit more about this later in the presentation. But the effluent or the leachate that is coming out of this operation, again, is then processed further in conventional hydrometallurgical process routes to produce the final metal. However, all of these processes, or most of them, generate some form of waste. And historically, one has sort of like not paid too much attention to that and saying as long as we put the waste into a safe disposal, and safe, I very much say here in inverted commas, then we don't have to worry about it. But that is really what I want to focus on in my talk today, is what happens, what kind of wastes are we dealing with, and what are the options for both disposal and regeneration of these wastes into useful products. So in mining, we have waste rock. You have to dig a shaft, or you have to clear away overburden material that contains no values and put them onto a waste disposal site. Flotation or concentration processes is where the key separation takes place. Often minerals are concentrated from ores by a factor of 50 or 100. And so the large portion of the material will actually go into a residue, a tailings impoundment. And we must bear in mind, this comes out of a comminution process, so this is very fine material. Leaching obviously will generate a leach residue, whether that is preceded by smelting and roasting or not. But then those are much smaller volumes, but quite often they contain quite a lot of hazardous residues. In heap leaching, we have the spent waste rock. So once the ore that's been piled on a heap has been leached, it no longer contains leachable material and can either be left behind or disposed of in a separate waste disposal. And smelting, obviously, as I said earlier, it separates between a metal and a non-valuable phase, and that phase is referred to as slag. And again, that is being then disposed of as a metallurgical waste. And finally, in the electrorefining, in the context of copper, you also have a waste that's referred to as anode slimes, and they have actually of particular interest because they are one particular waste stream that's been historically already recovered because it contains a lot of valuable metals as a byproduct of the value chain. So, as I now illustrated in this previous slide, the mineral beneficiation chain generates solid waste streams at every step. But historically, the focus has only been on recovering the major value metal phases in the process, often just a single metal or sometimes two value metals, and all the minor components that are associated with that mineral phase end up in waste streams. And furthermore, and this is also important to stress, even the target metal is never extracted 100%. Quite far from it, because you have so many steps on the way from the mine to the final metal product. Each of the process steps incurs losses, and those losses then reflect in the waste that you are producing in that particular process step. So, and that target metal is effectively now not recovered, but ends up in the waste material through process inefficiencies. In more recent times, and now I should say really this is already stretching back some 20, 30 years now, technological development has been and it continues to be made to recover minor metals, especially the so-called TIC metals that are attractive in high-tech applications, directly during the processing while they're still easily accessible in process solutions and hydrometallurgy in particular. And so you have a whole host of process retrofits that the major refiners have introduced precisely for the purpose of recovering the metals while they're still easily accessible in the process stream. I mentioned now that all the key minerals have certain metal associations. So there is no such thing as a pure mineral of one type or another. And because Aysha didn't know how to pronounce it, the word chalcopyrite is the classic copper mineral, but it does not occur in pure form. It is associated with a whole host of other metals and that need to be taken into account when you consider the recovery processes. So for example, this is often quite well represented through the so-called wheel of metals, an example of which I'll show you here on the slide, where you are starting off with the key metal or the carrier metal that is of interest in a particular phase, for example, with copper, and then a whole host of other elements that are associated with copper minerals processing, but only some of which are easily recovered, and that's the sort of gray inner circle, and many of which just disappear because they are too insignificant into waste stream or product process byproducts, and some of which are just not economic to recover at all. And so these bill of metal analyses have actually been done for many materials in order to identify where the opportunities for recovery of metals, either during processing or by reprocessing the wastes. Now, talking about wastes, I said earlier, so historically, that is just disposed of. So value metals are lost due to waste, due to uneconomic grade, to inefficient processing, to the lack of a commercial incentive for its recovery at the time, and I come back with some examples in a short while, the lack of a suitable technology to extract the value metal, and so these wastes are never just purely valueless. They may contain value fractions that have just not been recovered at the stage when they are disposed of. And so forms of disposal I show here in the slide, which has, depending on the nature of the material, I show here a waste rock deposit. So that's relatively coarse boulders that are piled on a big pile on the surface. You have various stockpiles that are built up in the operation. You may sometimes with the rock material also just fill it into, use it as actual landfill. So for example, filling in whole valleys and then covering the top of the material. And then the classic one, the most important and most fraught one in many ways are tailings dams. So this is just a nice aerial picture of the disposal, where you basically take the fine material that comes out of concentration processes and leach residues, and basically as a slurry, you let the slurry settle out, and the water is then decanted either through sucking it away or just seeping through the deposit as a whole, and you just build up layers and layers and layers of this deposited material. But all the surface disposal is important. Is very little of that material is backfilled, and most of the material is disposed in surface deposit with all their drawbacks. And I'm not going to go into much details because they're all well known. We had various presentations in this forum on the characterization and issues that are associated with the surface disposal of waste, such as surface runoff, acid rock drainage, leachate generation, dust, and the physical footprint and the potential for breach. So I'll just show here a few pictures to illustrate these effects. Catastrophic dam failure, where you basically have a breach of the dam and a lot of slurry just runs out into the countryside, often burying under it human settlements or agricultural land. And so we hear these stories on a regular basis. So there's frequently, that's associated, one of the main issues with waste disposal, but that is only the most obvious one. Mine dust, this is a historic picture, but nonetheless, it still occurs, particularly around tailings dams in Johannesburg, these classic dust clouds that arise and affect human settlements around where the dust comes from through respiratory and health issues. And again, we have already heard about this from our colleagues who work in the mine dust network. Then leachate generation. This is now the process of when incipient water, rainwater, seeps through the deposit and chemically interacts with the mineral that is contained therein, and then reaching groundwater levels, eventually reaching the groundwater, or surface runoff that will allow then channel itself, find its way into waterways, so that you get the classic sort of yellow boy discoloration of natural riverways from your classic blue to this yellow-brown color. And that is very much a real problem here in South Africa. And there is a lot of research underway, not to just understand it, but also how one can mitigate these effects. But the focus in this conversation is really just about the reprocessing from waste. And I said earlier already that some of this is already being done for different incentives. And I give a number of examples here. For example, the recovery from historic tailings, because you now have just better technology to more efficiently extract the material. For example, the ergo process that you had in the in Johannesburg on the East Rand, where basically all the tailings deposits are reclaimed, and both gold and copper are extracted by basically better liberation techniques and better leaching conditions than you had in the original process 100 years ago. There's also recovery from historic mine tailings due to a shift in economic value. So in a classic example here is cobalt, because now everyone is talking cobalt, everyone is after cobalt, but cobalt until 10 years ago was not a particularly important metal. There was enough supply as byproduct from conventional processing that people did not scramble for it. But with the whole battery storage and energy storage debate, copper has now become a hot commodity. And so there's an interest to recover copper from copper tailings, particularly in the DRC, where most copper deposits actually have a significant portion of cobalt in it that was originally removed from the flotation by flotation and is now being of great interest. Downstream recovery of value from process industries in a different industry. And I list just two examples here. There are many others. The one is the recovery of chromium from UG2 PGM tailings. So that obviously the incentive for the PGM processor is to get platinum group metals and the key base metals associated with it, copper and nickel, and a little bit of cobalt. But the tailings contain a substantial amount of chromium, which is of course interest to the ferroalloy industry. And so there are now examples of chromium being reprocessed from these PGM tailings in order to create a different commodity. Zinc is from steel making. Dust is another example. And I have here the many steel processes that use, particular ones that use scrap, have a considerable concentration of zinc in them from galvanizing. And the recovery of these processes is affected now in sometimes directly at the tail end of the more modern steel manufacturers. Finally, in-process recovery from waste streams. And that is what I alluded to earlier already when I talked about the anode slimes in copper refining. They contain gold and PGMs and exotic metals that are an attractive value proposition to recover straight away. So the copper industry has been recovering these metals from the anode slimes for a long time, but often also, again, it's done by subcontracted to other companies that focus on processing of these streams. There are many other opportunities, and some of them are under consideration, some are being actively pursued, but and this list is by no means exhaustive. So you have as a first, for example here, the recovery of gallium from aluminium process waste, the so-called red mud. Gallium is an important modern technology metal, but it is very significant concentrations in aluminium but it does not get recovered by the conventional aluminum process, the Bayer process, and can be extracted from the red mud phases. Rare earths from phosphogypsum, as well as titanium sand residues. So those are two very different waste streams from two very different industries. Both of them, rare earth, there are hardly any deposits that have concentrations of rare earth on their own to just process them directly. And so in most cases, the majority of rare earth are associated with other minerals. So phosphogypsum, which is generated from the sulfuric acid leaching of apatite. The apatite is a classic collector for rare earth metals that then do not report to the solution, but stay in the solid phase and are then precipitated by the gypsum that forms as a product of the phosphogypsum process. And they're very difficult to recover from that. Titanium sand residues, the beach sands that you process are enriched in order to extract ilmenite and zirconium phases, but the residue contains a significant portion of rare earths. PGMs from PGM flotation, tailings or low-grade rock. There is still very little underway in terms of trying to recover additional values from those flotation tailings, because the flotation might be in the order of 80 to 85% efficient, but the remaining 50% of PGM value, given the tonnages that the PGM industry produces, are still of quite significant value if one can find a suitable way of extracting them. Titanium from titanomagnetite. So titanomagnetite is mined for its vanadium content. The titanium that's a pyrometallurgical process, and the titanium reports to the slag. Cobalt from nickel processing slag. Similarly, the nickel was the attractive mineral phase in certain Southern African countries. The cobalt reported to the slag and was disposed of. And then, of course, the whole topic of urban mining, and I will not go into this in this particular conversation, but just suffice it to say that there are highly valuable metal phases contained in municipal waste, particularly in the so-called e-waste, from which the recovery would present a great opportunity. There are other opportunities for value recovery, and those are not metal related. And so I'm only going to touch on them briefly, such as carbon capture in carbonizable minerals, or building materials from waste products such as brick making from inerts or pigments from iron wastes. So one needs to look a bit what incentivizes the reprocessing, and that is really ultimately a look at the economics. Ultimately, it always boils down to the money. So there are a couple of aspects in waste processing that are favorable, such as that the feed material is already mined, so you don't have to incur costs or very marginal cost for extracting the rock or the minerals from the ground. It's easy to reclaim them from surface deposits. The feed material is often very finely ground. By mining or processing them, you would remove an environmental hazard that might be associated with but leaving it in the first surface deposit. And this way you actually avoid, by reprocessing it, negative disposal costs. What is less favorable in the context of reprocessing is that the metal grades are generally quite low, and the more recent that waste has been generated, the better the original process technology will have been, and the lower the target metal grades will become. The target metals might also be contained in refractory minerals. Refractory means they are not easily dissolved. They're not easily treated. You need high temperature process or very aggressive chemicals in order to solubilize these minerals in order to extract the value that you want. And the point is that there is no such thing as a process that doesn't generate some form of waste. And so whatever waste disposal you have at the end of all the processing needs to be a sustainable waste. It needs to be disposed of such a way that it does no longer form or pose a long-term hazard or threat to the society that lives around these deposits. So there is three economic drivers for the reprocessing of waste. The one, and I already alluded to that, is changing market demands. So cobalt for battery materials is the classic example because it was almost considered valueless previously, and in the last 20 years or so, suddenly demand has skyrocketed because there are very few primary deposits of cobalt, actually none. Cobalt is always mined together with copper. And so where it was previously separated away from the copper phase, it is now co-treated and co-extracted. But historically, there are significant amounts of tailings still available that contain extractable or economically attractive portions of copper. The second factor, driver, is the political climate or the concept of strategic resources. So here the classic example is the rare earth elements, which are at the moment mined to, the figures vary between 90 and 95% in China and refined there. And there have been sort of threats from China to basically exercise their monopoly and restrict the sale and into the market of rare earth products. They are strategic for high-tech products and electronics, and particularly also for the manufacture of rare earth magnets that you use in the processing of in windmills and for green energy generation. So there has been a scramble over the last 10 years to expand production outside of China, but there are not that many primary deposits for rare earths. And so one has to rely on, again, the interest is to extract them from secondary resources, such as the phosphogypsum that I mentioned earlier. The third driver is the so-called high residual value. So that's what I already said, and that really applies only for gold and PGMs, for the real value metals, where you dictate the price per ounce rather than per kilogram or ton. Because even if they occur in very small concentrations, their value, if you manage to extract them, their value would still be attractive to pursue this route. So that is also, for example, what drives the e-waste process is much more the value of the amount of gold that you would find on electronic circuit boards rather than the copper or other metal components, because although there is very little of it, its value still exceeds all the other value fractions combined. PGM tailings, for example, are in that context still an untapped resource, because no technology has yet been developed to extract them in that context. Different with gold, I mentioned the ergo process, and there are similar process operations throughout the world, but for the PGMs, that's still a very rare occurrence. So then let's move towards technologies that would be useful in the context of extracting waste. And as I already indicated, economics are key drivers. So technologies ideally should be low cost in order to enable the processing of waste that one would otherwise just leave alone. So, and to achieve that, one needs to look at a couple of characteristics that I've listed here. So these processes need to be small scale and scalable. So that is, they need to operate depending on the deposit side from the ton a day scale to the maybe 100 ton a day scale. But a lot of the industrial extractive processes, they only take, they start at the hundreds of tons. Well, depending on if you took the waste, the raw material, they start at the thousands of tons a day or the tens of thousands of tons a day scale. So one needs to be able to handle smaller streams, and yet the technology needs to still be efficient or cost efficient enough. It needs to be energy efficient. So energy intensive processing, particularly such as fine grinding or comminution processes and high temperature smelting need to be avoided in order to make these reprocessing processes viable. It needs to be water efficient, particularly in our local context. The problem is you have a significant loss of the water resource to tailings. About 30% of by volume of the tailings are made up of water. That's ultimately, some of it is recovered, but you want to make sure that you minimize the losses of water through the management of this material. You want to avoid specialist and material intensive equipment. So equipment that needs to be manufactured overseas, that cannot be manufactured locally, or relies on materials that are difficult to obtain. Or if you want to talk about hydrometallurgy, for example, pressure leaching equipment, that's speciality, and those are expensive. Autoclaves are costly to manufacture, whereas a tank, you can use a plastic tank that you find from a garden supplier. So those kind of thinking that needs to come into what defines low-cost process technology. Use common and non-expensive, non-toxic chemicals. And that is, for example, in the gold processing, people use cyanide. That is not necessarily something that you want to consider. You produce long-term benign residues or repurpose any waste material that you achieve. And here the concept of repurposing just means use all the waste for something, even if it's just for building materials, as I mentioned earlier. One aspect, and that's a bit difficult to perceive, but is the time, the compromise on time efficiency. In industrial extraction processes, normally you want to have a short, what we know as pipeline. You don't want to have processes that take a very long time, because you have a sunk cost up front, like the mining cost to obtain your feed material. And the longer it takes from that to produce from that the value metal that you can then sell, the more inefficient, financially inefficient your business works. In waste processing, that is not the issue, because the upfront mining is a relatively small cost of the value chain. The material is already in a processable form in most cases. And so therefore, time, if the process is a bit slower and takes longer to facilitate, that is not, from an economic perspective, as much of an issue. So one such technology is heap leaching. And it's, as Aysha indicated, is my area of expertise. But it is a low-cost extractive technology, because, as I showed you in the first slide, it is really just consists of piling the rocks on a big pile. You sprinkle solution on it. You put builders on an impermeable layer at the bottom, and you extract from the solution that runs through. You extract the metal going further. And then when the heap is exhausted, you can either leave it in place because you've got perfect drainage collection system already in place, or you remine it, reclaim it, and put it back onto a better disposal site. Both options exist in practice. I'm not going to go much through here the technology, the principles of heap leaching. As I just said, you have solution trickling through. You have air that's blown up in order to facilitate the oxidation of sulfide minerals. And you can, under certain circumstances, generate heat in the process. But the key thing is what comes out, trickles through at the bottom, is captured and collected in a carefully designed drainage system in order to process the material. A similar drainage system or is underliner system would be used in the context of modern the waste deposit design. So in a funny way, you design heaps already for disposal, because that's what happens after they are wasted. The second technology I want to touch on as a potential low-cost extractive technology is the field of bioleaching. So bioleaching actually makes use of a whole host of different microorganisms that can facilitate the dissolution of minerals. So here the example just shows one of them, which is the ferric leaching of sulfide minerals that releases, this example, copper into solution, and the reduced ferrous is then being regenerated by microorganisms using oxygen that is absorbed from the gas phase. But there are many other biological microorganisms that can facilitate the dissolution of other types of minerals. And there is a substantial amount of research going on in that area, trying to understand them. They are conducted in tank leaching processes, but under atmospheric condition. That is one of the attractivenesses, and at relatively low temperatures. And they can be scaled from a small laboratory scale to these 2,000 cubic meter tanks with these gigantic wheels that you see, and operated in any of these scales quite successfully. So then, to summarize just some of the key aspects of these two examples of low-cost technologies, and I acknowledge there are others, but time and focus is really not permitting me now to go into more detail. But the key thing here is that tank bioleaching operates at low temperatures and is a robust and well-established technology, and it uses organisms that are found naturally. They might be concentrated up through careful selection, but they're not some weird genetically engineered organisms. Those are naturally occurring organisms. So you make, in a way, nature work for you in this technology. Heap leaching, and interestingly enough, it can be combined with bioleaching, is also an established technology. It is mostly used for low-grade material in mines, and specifically for waste rock. And the particular attractiveness is that its operation alone is already fairly low maintenance, and the fact that the residues that you generate can actually be left in place if appropriately managed beyond the active operation of a heap. There are a number of alternative chemistries that one can also look at. So I'm talking specifically here now about hydrometallurgical processes, such as, and I guess in a way I've already set myself up to say that for the economic processes in general, you would look more at hydrometallurgical processes, precisely because they can operate at low temperatures rather than the pyrometallurgical high temperature processes. So you can use different chemistries. The conventional one is most of these processes sulfuric acid leaching, but here we're looking at other chemistries such as sodium chloride or chloride-rich solutions, cyanide, thiocyanate for gold, which is much less toxic than the classic cyanide, or magnesium sulfide instead of ammonia for rare earth processing. And then, but the leaching is just part of the technology because it brings the metals into solution, but you need to recover them from solution as well. So I mentioned there's solvent extraction as a classic technology, but solvent extraction uses highly specialist chemicals, and it's generally, they're very flammable, and some of them are quite toxic. So alternative technologies are also of interest here. And two to mention are ion exchange and bioabsorption. So again, a biologically facilitated process that allows the capture of metals into a solid or separatable phase from where you then can recover them. So now the question, coming back to the topic of my talk, is how does artisanal and small-scale mining fit in with this? And here I want to just take a step back and say, well, historically, all mining was small scale or artisanal. So if you look into Agricola's famous book, De Res Metallica, that clearly indicates all mining operation in the 15th century, when that book was focused, where small operations with a few people working there, digging in some small small scale mine. So the large scale mining is really something more that came in through the Industrial Revolution in the mid-19th century. And so the artisanal mining that we find, particularly in Africa to this day, is in many cases actually just what's left over and had been done for many periods, for a long period of time. But of course, it has a very negative image to issues such as child labor, slavery, gender issues, poor health and safety standard, rent seeking through mafias and dubious middlemen, exploitation, and so forth. But at the same time, one needs to acknowledge that a lot of these effects are actually created through economic and legal marginalization of such operations, or the outright prohibition. I mean, small artisanal mining is effectively called illegal mining here in South Africa. And that is, again, only a more recent development, because again, referring to the book by Agricola, and many stories, miners were a proud profession, even when they were operating on a very small scale under very hazardous condition. It was a proper profession, which people chose as their life career. So in a way, one needs to take a look back at it and saying, perhaps what we now call the illegal miner or the artisanal small-scale miners could actually become the regular SMEs, the small and medium enterprises of the mining world, if one facilitates them becoming legal and equips them, and this is the important part here, with the necessary technology to operate efficiently and in an organized manner. So I sort of positing that ASM is a good sort of a good start to the reformalization of the artisanal mining industry might be actually in the value recovery from wastes, because there's a couple of advantages here that in small scale operation, the operation only needs to offer, it is necessary to offer a marginal profit for the operator. But in order to do so, that operator would require assistance in the techno-economic assessment of whether a particular waste material is actually worth recovering or not. It might need, the industry might need incentivization through environmental levies, because the reprocessing of the waste will simultaneously remove the hazard of the established waste. There needs to be access to finance. And again, that would require an economic formalization. So a lot of the primitive technology, the mercury amalgamation technique that small scale miners use now, is because they just simply have no access to finance more appropriate, more efficient, and safer technologies. It can involve here the opportunity for the promotion of low-cost technologies and know-how. You can build mobile and scalable plants. And these are all the conditions that are listed in my earlier slide that would actually fall on a very fertile ground in this particular context. And then, of course, there's the need to legally formalize the industry through licensing, ownerships, and an establishment of liabilities. So that is really just a vision how I see this going forward into the future. And it is just a perspective that I'm presenting here. It's not saying this is what should happen, but it is clearly a very concerted effort to look both at the technology and the establishment of this technology, and looking at particularly at the marginalized ASM sector as an opportunity to develop these technologies to recover value from waste and render the wastes themselves less hazardous or even obsolete. And so a lot of the work that is that I touched on, and a lot of the understanding is backed up by the research work that is going on and the minerals to metals in the broader UCT community. So I want to list a few here just for acknowledgement. The Center of Bioprocess Research, CIBA, who have been for decades active in bioleaching, bioremediation, biorecovery, and with a specific focus also on recovery from waste materials. There's the Future Water Institute, and we heard some presentations from them recently, particularly understanding the water mine waste connect that I alluded to. And I think even in the ASM context and the waste recovery context, one needs to always keep a keen eye on what about the water. Then the Minerals to Metals initiative itself, which, as we illustrated some time ago in the forum talk, is really a network of different projects and initiatives and groupings that do collaborative work on the extraction and on the minerals to metals value chain. So within that, we have, for example, the Mine Dust Research Network. We reap the repurposing of mine waste. There's some research projects going on. There's urban mining, There's equipping the artisanal small-scale mining sector with alternative technology choices, so investigating those in that context. Evaluation of the Sustainable Development Goals in mining. So all of these points, we have already seen some presentations in the forum, and we'll take this further in going forward. Then there's the hydrometallurgy research group, which I also head, which is really focused on heap leaching processes, on ion exchange, and the analysis of flow sheets for the identification of such opportunities for value recovery. And as well as the Center for Minerals Research, who are doing some excellent work around mineralogy, also of waste materials, in order to say certain processes won't work because the mineralogy of the target metal does not allow that extraction. And finally, the Mineral Law in Africa position that the initiative that really looks at the value and the legal framework that revolves around mining, especially in the artisanal small-scale sector, but also in terms of incentivizing and operating the research around recovery. So with that, I thank you. I didn't go too much over time, and I'm very happy to take some questions.
Thank you so much, Jochen. That was a brilliant presentation, and it really does function well between those who have very little technical knowledge and those that are a little bit more in tune with, you know, the chemical engineering side of things. So thank you so much for yeah, spoon feeding some of it for me. I really do appreciate that, alongside the more technical aspects. So we have one question. Firstly, just congratulations on the presentation and generally well received. The question is, are there any commercial operations utilizing bioleaching to reprocess mine tailings?
Yeah, thank you for the question. And in fact, I showed a picture of the bioleaching tanks that are in operation, or I think they are now decommissioned, but for a long time here in this picture, these large tanks are from the Kasese bioleaching plant. They are reprocessing a cobaltiferous pyritic tailings that were left behind after the extraction of the relevant copper value from that then was fed into a smelter. So the tailings have been sitting there for, that operation dates back to the 1950s or so. And then in the 1990s, this operation was commissioned to extract the cobalt value. And it was perhaps a little premature because the value of cobalt skyrocketed really only towards the end of life of this particular operation. Other operations look particularly at gold tailings. So you might find that pyritic tailings that contain still gold because it's particularly arsenopyrite, insufficient extraction, where then it is worth to re-leach and liberate the gold from these particular materials. That's the two examples I can think of offhand, but there are a few others. But admittedly, it's still a technology that's evolving, and I think the research that's going on to support this is probably is very likely to show other opportunities in the near future.
Thanks, Jochen. There's another question from Petersen. Is it not the informal nature of artisanal mining that makes it worthwhile for small-scale miners, so that the current structures of regulation, licensing, taxation, safety auditing, etc., would make it unsustainable and only legal operations would prevail?
It's a good question. And I believe the solution lies in a golden middle. It is correct. Overregulating would basically take the incentive, the spontaneity for small scale and perhaps sometimes even quite inventive operation away. But at the same time, not regulating at all will cause a lot of people to take too much free license and maybe just extract the value and leave behind a mess. That's the big concern. So I believe there is a way, and this is very much what our research, particularly with Milia and yourself, Aysha, is trying to look at, is saying how can we achieve both a reasonable amount of compliance on with how this process is operated without over-regulating and overtaxing the system, so that it actually becomes not viable.
Thanks, Jochen. Many compliments from the chat and the Q&A section. We've got another question here. What is your prediction for the next improvement of heap leaching operations, especially in gold and copper mining?
I think the key thing in heap leaching, and as I said, I've done a lot of work, is that a lot of people are frustrated by the slowness of the process and the fact that value fraction is extracted at a pretty slow rate. And I think there is an optimization of making these heaps by fully understanding the mechanisms of how heaps tick. And I think that understanding is only still a little bit in its infancy to make sure that you optimize the extraction. I refer back to an example that when I started working on heap leaching, we did an experimental setup that was back in Vancouver where I did my postdoc, where we managed to extract over 90% of the metal phase from the ore within 4 months, and in a laboratory setting, in a heap leach setting. So the real live operation took over a year to achieve the same. So my argument, a lot of people saying that's just how it is, and my argument is, and a lot of our research has shown that if you construct and operate these heaps under appropriate and carefully controlled conditions, you can, in actual fact, achieve such much higher extraction rates than the practical operation allows. But there is a certain reluctance in industry, because these operations are so large scale, to quickly change practice and try something different. So the improvements that in heap leaching are a process that have occurred over the last 20 years that I've been involved with it. But nowadays, heaps operate already a lot better than they did 20 years ago, because generally the understanding and the operation of these processes has substantially improved.
Thanks, Jochen. We have a question here from Neil. Do you not map out sorry, this is more a statement. You do not map out the toxicity changes along the process, or you do not map it extensively. Do you not feel that this is highly unethical to place such vulnerable people in the direct path of the hardships faced of such toxicity? This explanation...
Sorry, Aysha, sorry, I need to turn up my volume. I can't quite hear the question. Just give me a second.
You can also see the question. It's not in the Q&A section, it's in the chat.
That's not the issue. I'm trying to get into out of. So I have to just quickly stop sharing because I can't get to my volume button. That's all. So please just repeat the question.
Okay. You do not map out the toxicity changes along the process, or you do not map it extensively. Do you feel that it is highly unethical to place such vulnerable people in the direct path or face these hardships of the toxicity? This explanation sounds similar to when we placed people in front of asbestos, because they could too benefit. Toxicity mapping is what I would recommend. With this done, then the ILO regulations will already be exceeded. Then to mitigate this risk, are you not then ramping up the costs of the operation and eventually leaving you with exactly where you are, a waste stream that is in any event a sub-economic targets?
It's a fair question to ask, and I agree that one in the context of evaluating any particular option is one does need to look at the toxicity, both in terms of the products that you're handling or the process that you're operating and the waste products, if there are secondary wastes that you're leaving behind. But I think it's dangerous to generalize that to the extent to say I think it boils down and is similar to analyzing value chains just in terms of the commodity, because it depends very much on the mineral. It depends very much on the previous operation. It depends very much on the age, for example, of the waste material, because sometimes material alter weather. And so what was originally disposed has now already substantially changed. But that said, it is definitely a valid and important point to make, whether the handling, the hazard, basically hazard potential of the material that you're processing is not in some way compromised or exposing people to risks that unduly. So yes, I take the point. Thank you very much. And I think that is in expanding the whole concept that I try to sort of map out here, certainly of some value.
Thanks, Jochen. So we have gone over time 2 minutes, but we have a fair amount of questions. So I would like to run through some of them, maybe take another 5 to 10 minutes if it's fine with Camilla, if we're okay with time with our hosts. That's fine, Aysha. Okay, thank you. Okay, so we've got a question from Cledwin. ASM relies on rapid results as the individuals involved are predominantly on the move. How will alternative technologies offer the same perceived value?
Sorry, I'm just trying to, switching between Q&A and I'm not quite sure what is meant here by on the move. You mean because the artisanal miners are essentially an itinerant trade that move from site to site? That is, if that's what is meant by it, then the answer, I have actually mentioned that in my talk, talking about scalable technologies and mobile and even possibly mobile technologies. So it's stuff that can actually be rigged down and put on the back of a truck and moved to a different site. And that is a very pertinent concept, because particularly many historic waste deposits are just small scale, and they would possibly only allow processing for a few years before the value is extracted to completion. And so the need to then not write off your equipment, however limited it is, but rather be able to move it around, is certainly something that needs to be taken into consideration. But for that to work, obviously it needs to be at a scale small enough to fit on the back of a truck or into a container, a set of containers, to be movable.
Thanks, Jochen. So we have a question in response to the answer you gave for the first question. Might you have an idea of the reduction in the all-in sustaining cost, AISC, of the bioleaching tailings compared with the original process that generated the tailings?
Not entirely clear. So the answer is actually not really. But I think it's a good question in terms of saying, could one use the bioleaching of the tailings as a motivation to run bioleaching as a process right from the outset? And that is certainly a consideration worth making. But the issue is that if the tailings have already been generated, and this is particularly what I'm focusing on, the historic tailings that still offer value for recovery. And so it's not much point in comparing the costs of a recovery process in that sense. Yes, it's end of pipe treatment, which is not desirable, but the point is the waste is already there. So it's not much point to compare it to the process that generated the waste, because it's only relevant if you look at future operations. If you design a process that you want to develop in the future, that you then say, well, you weigh up different options of treating the waste or handling the waste as an end of pipe treatment rather than avoiding the waste through a different type of process in the first place. I am not sure I'm answering this question correctly, but that's how I understand it.
So we have a question from Yakulo. Do you think bioleaching or heap leaching will be used by artisanal miners? Do you think it is scalable to that level for that skill level?
Yes, particularly heap leaching is already practiced by artisanal miners. I have quite a bit of anecdotal information about this in Zimbabwe and in other countries where people are operating small-scale heaps. Or I mean, you can make them just as like a little pile of rocks, you know, that you put onto a plastic sheet. It isn't really any scale limitation that how you operate that, but the extent to which they operated in a sound manner, particularly to collect runoff or to make sure that the leachate is collected appropriately and processed appropriately, that I can't comment on, but it's definitely scalable. Bioleaching, I see no reason why not. I mean, when we do small-scale tank or heap bioleaching, we at a pilot scale, that is perfectly feasible. And it's scalable. That's in actual fact, those bio-leach processes that have been commercialized have been carefully scaled up from the liter to the 10 liter to the 100 to the 1,000 liter scale and quite successfully. So they can be made to operate at each of these scales. Where there's the economic cutoff, that I can't comment. But certainly on the heap leaching side, it's being done at very small scale.
Sorry, we have a comment from Petrus regarding the previous question that he asked. I think the ability of heap leach fine slimes would be another breakthrough, i.e. without extreme binder costs.
Yeah, Petrus, you're right. I thought of including a discussion of how you could make fines heap leachable, but in the interest of time, I left it out of the presentation. But there is certainly a consideration that through correct type of agglomeration, that you basically make a fine material heap leachable, if you can use that term, through basically making the material coarser again, then that would indeed be a breakthrough.
So we have a question from Richard. What has been the latest progress into increases in recovery in bioleaching of chalcopyrite?
Chalcopyrite.
Chalco. I love that I read copyright in the middle, and that's such a classic like law. Anyway, so it just shows you from the different perspectives, you will read things differently.
Yeah. So chalcopyrite, for those in the know, that's the copper iron sulfide mineral. It's the most dominant phase of a copper mineral, and a lot of the mines that and it's notoriously refractory to most leaching processes, and it is generally still treated in high temperature smelting type processes. Now, bioleaching has actually, amongst the chemical methods, showed quite a bit of success in the context of a high temperature, high temperature microorganisms, high temperature just being in the order of 60 to 80 degrees, so-called thermophile microorganisms, which somehow manage to create conditions that are very favorable to chalcopyrite leaching. And the process is here in a tank process that has been demonstrated. And in fact, there has been an industrial demonstration plant for the tank bioleaching of chalcopyrite, which was discontinued primarily for the reason, not because the bioleaching wasn't efficient, but because the technology, in order to achieve enough of a rate, and this leads me back to this time effect that I mentioned, was that the process was too slow, and in order to accelerate it, you needed to inject pure oxygen rather than just air, and that made the process just too costly to operate. And also you need to operate these tank bioleaching processes at a more dilute phase, so you have to build these much bigger tanks. So that all these cost issues that come into that are at that level. But that is not to say that the principle of thermophile bioleaching is well, of chalcopyrite is well established, and has also been demonstrated in heaps. And the interesting thing here is, of course, you need to manage those heaps quite carefully to achieve and maintain the temperatures necessary for those thermophile bacteria to survive. It has been shown to be possible, but it's, again, because these heaps are such large operations, quite tricky to sort of maintain the technical control of this temperature regimes. And there's still a lot of research effort going on in that regard.
Okay, last question for the day. Thank you so much, Jochen, for sticking with us a little bit longer than intended. So from Eric, relative to dual carbonization, CO2 storage, and metal recovery, what metal groups / tails are favorable? Which leaching agent has been tested?
Okay, I mean, so basically, for carbonization, you would need any mineral that is forms insoluble carbonates, which is particularly in the sort of earth alkali bracket, but also some of the base metals, particularly iron, can form carbonate materials. So those are materials that you then in most cases happy to waste, so to speak, so to not wanting to recover. Whereas, of course, base metals and those metal values you don't want to precipitate with carbon dioxide, because that they have a higher value if you actually recover them. But that said, it's an interesting question, because if you operate in acid leach processes that dissolve minerals or the gangue minerals to a significant extent, that to release such things as calcium and magnesium, which are fantastic agents for the carbonization, or you even use acid mine drainage, where the iron is an unwanted component, and combine that with the carbonization process, then that is a route that can work. But the leaching agent is really just an acid that can allow the dissolution of gangue minerals, and then the subsequent separation of these gangue phases in aqueous solution, so that you can contact them with carbonate to affect precipitation.
Okay, thank you so much, Jochen, for being with us today and for the incredible presentation. And I would like to extend a thank you to all the attendees who asked questions and participated in the session. We will definitely send through the presentations. I know people have been asking me, and I've not lost, do not lose faith. I will send through the presentations as soon as we have all of the videos edited, and yeah, you're going to get a huge lump of information sent to you soon once everything is brought together. So thank you so much, and I will see you all next week, Wednesday.
Thank you very much also for attending and listening to my talk. And I hope I might work with some of you in the future.